This is Dr. Harris, and this tutorial is going to go over the design of a prime number detector and an even-odd detector. We start off with a new project in Vivado, and we go all the way until we actually download it to the board and test it. So I've set up this Vivado folder, so you're going to double-click that. The important file in here to start with is run Vivado script here. So double-click this. You should see this pop up telling you it's doing stuff. So it will take a few minutes for this to open up. So once this opens up, you can go ahead and click on File, Project. The wizard will kind of guide you through things. So what do we want to call this? I'm going to call this, this particular project is a prime number detector and an even odd number detector. So prime is what I'll call it, and you don't need to capitalize anything. And it's also best if you do need help from me, just type your name in there, your last name. No spaces in the file name. We're going to do RTL project. We are going to make sure that we select VHDL here and VHDL there, because we are coding in VHDL code. If you don't do this, your project will not work and you will need to start over. We are not going to add, well, yeah, we could add our constraints file already. So I've clicked add file here, and in our Vivado folder, which is home, OS boxes, desktop, Vivado, there's this file here, master constraints file. So I'm going to click that, and then next. Then it's asking what is our chip. This is specifically for the Basis 3 board that we are using here. And so what I'm looking for is the particular chip number. So I'm going to look at the package area, and I'm going to choose CPG 236, speed -1. We are the XC7A35T, and we're going to select the middle selection here because we have 41,000 flip-flops. That's the easy way to look at it. And you'll do this for every single project that you use. So remember CPG 236, speed -1, and just choose the center option there. Click next, and then this tells you a summary, and then click finish. While this initializes the project, I'm going to show you the concepts of what we're doing. So basically we are going to be generating the code for a prime number detector, and we're going to do this in VHDL code. So VHDL code has two sections. It has an entity and an architecture. You define the entity, which is just a black box. It has a name, in this case prime. It has inputs and it has outputs typically. In our case, we're going to have inputs, and the way to read this is 3 down to 0. So there's actually 4 bits of data there, and you can see the input has a little slash across it, and that usually means that it's a wider than single bit input. And then our output is going to be a single bit, and that's called is prime. I'm going to be able to type in, or rather use switches to put in numbers between 0 and 15 in binary. And if it is a prime number, I want the is prime output to be a 1. If it is not a prime number, it should be a 0. So this is now back to Vivado, where it has loaded up our basic project. We need to add a source, and so you can click add source here, it's going to be a design source. And we are going to create the file, and I'm going to call this file prime. Again, making sure that it's VHDL. Click OK, and then finish. This window pops up, which allows me to set up my inputs and outputs through this wizard. So if you remember, I said that I have an input, and I'm going to call it input. The direction, it's an input, not an output. And it is a bus, which means that it's more than 1 bit. And it will be 3 down to 0. Then I have a output called isPrime, which is an out, and it's only a single bit, so it is not a bus. If you remember, I can flash this back to this design. So it's called prime. It's got an input, which is 3 down to 0. It's a bus, that's what the slash here means. isPrime is a single bit, and that's an output. So I'm going to go back here and click OK. And it's going to automatically generate the code for my entity. Now, I don't expect any of you to know anything about VHDL at this point. It's just a hardware description language. It's a code, but it doesn't execute sequentially like C code or anything like that. You're actually using this code to describe hardware. So you're describing a circuit. And we could describe it as AND gates and OR gates and how they are connected, and sometimes we do that, and that's called structural VHDL code. However, in our case, we're going to simplify this, and we're just going to describe the behavior that we want. And so I'm going to double click on this prime here, and that's going to open up the file. And this is what the basics of our VHDL code should look like. We've got our libraries up here at the top. Comments are started with this double dash. Sometimes we will actually uncomment this arithmetic library in later assignments. That's usually a stumbling block for a lot of folks. But it's written the code for our entity. So it says entity prime, which is what we called this file, is, and then it describes the ports. I have one port that's called input, which is a in. It is a standard logic vector, which is another way of saying a bus or a multiple bit number, and it is 3 down to 0. That's exactly what we described earlier in our picture. And then we have an output called isPrime, which is an out, and it is a standard logic. Standard logic is a single bit. It is not a vector. It's not more than 1 bit. Then we have this section here, architecture, behavioral of prime is and begin. And what this basically is, the architecture is the description of the circuit that we're trying to build here. Right here, this says behavioral. This doesn't necessarily mean it's behavioral style VHDL code. It could be structural style, but this is just a variable name, and typically we describe it as this is what it does. This is what the prime entity does. So in here we'll go the guts of our black box. And we have to say of prime. And as we say of prime, this is defining this particular entity. And then we have the section that says begin. Sometimes you might declare certain things on top of begin, but in this particular case, we're not going to need to do that. And after begin, this is where your code is going to go that describes how this thing will function. So in our case, what we're going to look at is simply writing the code for something that detects prime numbers. So if we're going to have 4 bits on our input, that means we can count from 0, 0, 0, 0 to 1, 1, 1, 1. So 0 to 15. The prime numbers that are in that range are 2, 3, 5, 7, 11, and 13. Now recall what a prime number is. A prime number can only be divided by itself and the number 1. And so, using your logic, you can try to figure out whether or not this is going to actually be the right list. You know, should we count 1? Should we count 0? Well, are they defined as a prime number or not? For this thing to function correctly, you're going to need to know, is it a prime number or not? So, to write the code that actually will output a 1 when my input is any of these numbers, I'm going to say the output value, the name that we gave our output is called isPrime. And I'm going to use this symbol, which is kind of like an equal sign whenever you're using C code, but really the way I term it is I say isPrime gets the value of, and then I'm going to define the cases in which it's going to be a 1. So it gets the value of a 1 when my input is equal to 0, 0, 1, 0. So this is the binary value for the number 2. And so that's what I'm defining here is this section. But I don't want it to just do that. So that's going to be 1. And I'll just make the note that this is 2. And I want to basically do this again. So for 3, when my input is equal to 0, 0, 1, 1. And I'm going to actually do this for each of these. Now something to note is if you have a single bit value, you just use a single tick mark there, a single little apostrophe. If you have multiple bits, so a vector, you will use parentheses here and quote marks, the double quote marks, not parentheses. So when you have a single bit, you will use a single tick mark or an apostrophe. If you have multiple bits, you will use double quotes. So I'm going to continue to do this. And in fact, what I can do at this point, I've already got some code. So I'm going to copy and paste this. And I'm going to just change these values. So just to format this a little nicer here. So in this one, I'm going to put, this is 5, so 0, 1, 0, 1. In this one, I'm going to put 7, so 0, 1, 1, 1. And then I'm going to copy for the last 2, just copy these and paste again. And then I'm going to put the value for 11 here. So that's 1, 0, 1, 1. So that is 11. And the value for 13, 1, 1, 0, 1. Here. I'm going to go back and just clean up my comments. It's very critical to make comments in this code. And then finally, since this is kind of an if-else statement, I need to put what it should be, what this value should get, what this output should show if none of these cases are true. So I just simply say otherwise it's going to get a 0. Make sure you hit the 0, not the O here. And then you're going to end this with a semicolon. Once you've done this, click Save. And you may have noticed red marks that appeared over here in this column. This shows you where there's a syntax error. And so we have now fixed it. There's no syntax errors. And we can actually go ahead and synthesize this if we'd like to. And synthesizing will basically almost like compile it for you. And so if there are any errors, they would show up down here. The key things to note are the tickle console and the messages. Sometimes the logs are important as well. But if there's any errors or warnings, they typically will show up here. And you can debug to figure out, where the error happened, and we can go back from there. So the next thing that I want to do, we've got the prime number detector, but I also wanted to detect whether a number was even or odd. And so I'm going to need another entity, and I'm going to call this even odd. It's going to have the same 4-bit input 3 down to 0, and I'm going to actually have 2 different single-bit outputs. I'm going to have one called even and one called odd, and I'm going to attach LEDs to these later. And so if the number is an even number, it will show even. If it's an odd number, it'll show odd. So the way that we do that, we simply add a new source, create a new design source, create a file. I'm going to call it even odd, and I don't really need that to be capitalized. You can capitalize it. We'll keep it that way. Click OK and finish. And again, it's going to ask us, what are your inputs? Well, we want a input called input, which is a bus of 3 down to 0. Then we're going to have an output called even. And an output called odd. Make it an output and allow it to generate the code for us. It may take a moment, but it will pop up here. You can always make sure it says updating. So I double click even odd, and it has again generated the entity for me. So I have a object, a black box called even odd. I have an input that is a vector 3 down to 0, and this is named input. It could be named anything, but the thing that makes it an input is this little piece right here. So input colon in is the direction. Then I have an output, which is a single bit. Its name is even. It is an output, and this defines it as a single bit. And then I have an odd output that is a single bit. And now I need to add the code for the determination of whether or not the number is even or odd. So again, I'm going to flip switches, which are going to be on my input, and I'm having LEDs display whether or not the number is even or whether it's odd. And so how do we detect that a value, a binary number, is even or odd? Well, there's a lot of ways to do it, but the most simple way is to look at the least significant bit of that number. Numbers like 2, 4, 6, 8, they always have a 0 in their least significant bit because that is the 2 to the power of 0 place. And so if you have a 0 there, it's going to be an even number. But if you have an odd number, then your 2 to the power of 0 place will have a 1 in it. So basically what I'm going to do is just say, all right, well, odd numbers, the odd output is going to get the value of my input's least significant bit. And so that's what this code looks like. So odd gets the value of input's least significant bit, the 0th bit. And then even is actually the opposite of that, right? It's the inverse. So if it isn't odd, it must be even. So I write my even output gets the value of not input 0. And what this defines is I am inverting whatever my least significant bit is. So if it's a 0, I'm going to invert it to a 1, and then that 1 is going to get stored on even. If that value is a 0, then a 0 gets placed on odd. So in even numbers, only the even LED lights up. On odd numbers, only the odd LED lights up. Again, these are just the inverse of one another. So I'm going to click Save. And I'm going to start moving on to the next piece here. And so the next piece is we actually have two different things here. We now have a even odd and we have a prime. And what we need to do is put them inside a larger element. And this larger element I'm going to call my top schematic or my top file. So I'm going to create a new file called top. I'm going to make my input called switches, SW, 3 down to 0, so it's a 4-bit number. My outputs are going to be LED 2 down to 0. So I've got 3 separate LEDs and I'm addressing them individually here, but I could have just defined them just like I did my switches. Once I've defined this black box, I could start looking at putting these guts inside here. And so I'll need to bring in my prime number as a component and my even odd as a component, and then we'll create instances of them and use them. Add a new design source. I am going to create a file called top. Finish. And again, my inputs, it's called switches. It's an input. It's a bus of 3 down to 0. And then my outputs, I'm going to actually define them as a bus because that's how they're set up on our board. And I'm going to say 2 down to 0 because I only have 3 values. And then if this ever happens where it just tries to create a new one, you can delete that line with the negative sign there. And I click OK. It's going to generate our code for us, our starting code of the black box entity. Again, watch the updating icon here to see when that's done. And one thing that's really key here is if you notice the prime number has this little icon next to it. It kind of looks like a triangle. And what this is this sets whatever the top level schematic is. And so I could right click on my top and say set as top. And that will allow this to now be the top schematic officially. Just because I named it top doesn't make it the top. So it takes a moment for that to occur. And now I'm going to open up my top schematic. I'm going to get a little space here if I can. So again, our top entity, it's a black box. It's called top. It has a port called switch, which is an input, which is a standard logic vector, 3 down to 0, so a 4-bit input. Then I have a port called LED, which is an output, which is a standard logic vector, 2 down to 0. I need to start filling out my architecture. And previously, we just started in the begin area. We just started coding right there. But what we're going to do this time is I need to bring in my even odd and my prime because it doesn't know those really exist yet. So currently it knows of things like an AND gate, an OR gate, an inverter. These are things that are in my toolbox and I can utilize those. Just like I did in my even odd, I could just say not something and it will know that I'm using an inverter. However, I created what a prime object is. This is a new thing. It never existed before in this toolbox. Even odd is also a new thing that it never had before. So I need to define what these things actually are as far as their connections whenever I wire up a schematic. So the easiest way to do this is to go back to our prime, and I'm going to copy the entity and paste it into my top schematic. But I can't just leave it like this. It's actually showing me right here there's an error. So this shouldn't be called entity. I've already defined the entity. I need to call this a component. And I can get rid of the is there. And technically you could say end prime, but I usually like saying end component just to be kind of a overarching thing here. And it's important that I do this because what this does is it says, hey, I want to use a thing named prime. This is what it looks like. It's got an input of 3 down to 0 named input. It has an output of 1 bit called is prime. And it just tells me that this is now in my toolbox. I'm going to do the exact same thing with my even odd entity. So I'm going to copy this. And again, this has to occur before the begin. I'm going to change entity to component. I'm going to delete the is, and I'm going to say end component. The reason I recommend just copying and pasting is it's very easy to have a typo whenever you're retyping this, and it will just you'll just have errors that you can't figure out. So go ahead, copy paste, change entity to component, say end component, and delete the is off of the initial line there, and you should be good to go. So now I've told this code, the top, that I have things called prime and even odd that I'd like to use. I have a blueprint of those. Down here, after the begin, this is where the actual code is going to go. What I want to do is create what they call an instance of these components. So I have the blueprint. This is the blueprint right here. I want to actually have a particular one. And what's really good about VHDL is you can actually have multiple prime objects in here. And so each one of them is called an instance. And you can instantiate them, or create an instance of them, and name each of these individually so that you know which one you're dealing with. Well, we're only going to need one. However, we still need to do an instantiation of it. And so I'm going to call this prime insta0. And I'm going to put a colon. And if you do it right, it's going to highlight it as green. But basically, this is just a label. I'm using insta0 because insta0, just because that's what I had on my graphic when I showed you before. And so once I make this is just going to label that I'm using this prime. I'm going to say I'm using a prime, and I'm going to do what's called a port map. And what a port map does is it allows me to wire things up. So I'm going to say the prime has this thing called input. What do I want that to be wired to? Well, I'm going to wire that to my top level switch. Now, you might say, that's interesting. How do I even know to do that? If you look back here, here's my prime instance. I have my input, and it is wired to my top level switch. So this is what I'm doing here. Top level switch goes into my input of my prime instance, which I have named prime insta0. And then my is prime output is going to be wired up to my least significant LED. So I just simply go back to my code here. And when you're doing a port map, you end the line with a comma, not a semicolon. And then you say is prime is going to connect to LED 0. And then we're going to end our port map. And so if you look here, there's the open bracket of the port map, and here's the closing bracket of the port map. Notice there's also no semicolon or comma on the last line here. This is just syntax of VHDL. The next step is I need to create an instance of my even-odd. So I'm going to call it even-odd underscore insta0. Again, I'm doing the insta0 because you can actually have a variety of numbers of these things. You can have 10, 20, whatever you want. You need to be able to address individual ones. You can actually name these things whatever you want. That's just a variable name. So you can call it Bob and Jane or whatever. But then we're going to bring in the fact that we are using an even-odd. So that is the actual component that we're using, and we're going to do a port map for that as well. And if we look at what the even-odds ports are, we have input, we have even, we have odd. Again, if we look at our schematic here, our input is going to be connected to the top level switches. Our even output is going to LED 1, and our odd output goes to LED 2. So that's fairly simple to do. So we're just going to type our input connects to switches. Now you might note that I'm not putting 3 down to 0 here or 3 down to 0 there. I don't have to because these are both the same size. So these 4 bits are going to connect to those 4 bits, and it knows that bit 0 on input is going to connect to bit 0 on the switch. Bit 1 on the input connects to bit 1 on the switch, and so forth. So I don't really have to define that. The next thing is my even pin, or my even port here, is an output, and I want that to connect to LED 1. And my odd is a port. I want it to connect to LED 2. I'm going to close the bracket and a semicolon. And what I've just done here is I have structurally built the schematic that I just showed you. At this point, anytime you see the star, that means the file's not saved. So at this point, I'm going to save this. And then I'm going to run synthesis. This is going to pop up and ask you, are you sure you want to do this? How are you going to set this thing up? You can actually say don't show this again, but just click OK. It'll begin synthesizing these files. Now what I recommend, don't create all 3 files individually and then try to synthesize. Synthesize as you go. It's just like in C code when you try to compile, you'll find errors when you synthesize, and then you can debug those errors along the way. Don't write your entire code and just assume it's going to work, and then you have all these errors that you can't debug. When you run synthesis, it's going to take a while. It looks like this whenever it's in process. But again, what it's actually doing is it's kind of compiling all of this to a certain degree. Or at least that's what you can think of. Doesn't really, I guess it compiles if you're simulating, but it's really defining what the hardware should be if you're making hardware, or what the lookup table should be if you're using FPGA. While this is happening, I'll discuss our next step. So, if this is the thing that we just built, we built a top file, the connection will go to the switches, the outputs will go to LEDs. I need to verify that this thing is going to work like I expect it to. One way to do that, before I actually go through the process of making a chip, which is very, very expensive, is to simulate it. And so the way that we do this is we have a thing called a test bench file. And when you do the test bench file, what we're going to do is we're going to actually use the top level schematic here as a component within my larger level test bench. Now a test bench doesn't actually have any external inputs or outputs involved here. So there's no inputs or outputs on the edges. What it does have is the ability for us to connect values to the inputs of any components we have. And we can also read the values of any outputs of those components. And so what we're going to actually do is we want to force values on switches, the inputs to our top schematic, to be 0, 1, 2, 3, 4, all the way up to 15. And for each of these inputs, we want to read what the values of the LEDs are going to be showing. So one way that we can do that is by writing this test bench file. So I've switched back here, and you can see I've got a new pop-up. When the synthesis is complete, it will say it's completed. For the moment, I'm just going to cancel because what I would like to do is I'd like to add that test bench. So I'm going to go up here to add sources, and this time I'm going to specifically click I want to add a simulation source, not a design source. I'm going to create file, name it top_TB for top test bench. Click OK. And when you're doing a test bench, again, there's no inputs or outputs. So when this window pops up here, we don't need to have anything in our entity. And it says, are you sure? Yes. So it takes it a moment to set up your simulation source. So I'm going to open up, you go to simulation sources, top_TB. I'm going to open that file up and start editing. So here you see we do not have anything in our entity because we don't have inputs or outputs on the actual test bench. And so if I look back here, this is our test bench. There are no outputs on this side. There are no inputs on this side. And so that's perfectly fine. Now, one thing that we are going to need to do, this is very, very important. We are going to use the numeric library. And so you have to uncomment this line 27 here. So just simply delete the 2 dashes, and then we're good to start coding. So I mentioned before, in our architecture of the test bench, we need to bring in a top component. So we have our top file, we need to create a component of that. Anytime that we are bringing in a component, I'm just going to copy the entity so I don't have to retype it. And I'm going to paste it in here. So components are declared after architecture and before begin. Remember, this says component that is goes away. And then down here, I'm just going to write end component. And then I'm going to actually do something a little bit different. I'm going to create what we call signals. By manipulating these signals, that is how I'm going to be able to actually force values on my input, and that's how I'm actually going to read values off my output. So a signal is literally just a wire when you're looking at the schematic. And so I'm just going to say, I'm going to connect this wire to this wire, and this wire to this input, and so forth. So what I'm going to call each of these things is, basically I'm going to call my inputs what I'm going to connect them to. So I'm going to call this, and this is going to be connected to switches. So I'm going to call this switch signal. And I need to define how big a signal is. Now, you don't have to put in or out for signals. In fact, you shouldn't. But you should put how big the signal should be, how many bits. So in this case, it's a 4-bit signal. Next, I want to have a signal for my LEDs. So LED signal. Put the colon, std, vector, standard logic vector. And our LEDs are 2 down to 0. Because we're using LED 0, LED 1, and LED 2. And then I'm going to add this extra one here, signal counter. And I'm going to make this an unsigned number. 3 down to 0. And I'm going to set it to start at all zeros. So don't worry too much. Fix that. Don't worry too much about some of this information. It's not really, you don't have to understand it at the moment, just to actually do it. So let me see here. I've got a syntax error. It says unsigned is not declared. That's because I misspelled unsigned. So there we go. That should have fixed that. Now it says, it went away. Okay. All right, so now I have my component top, and I've got some signals. And a component is useless unless you instantiate it or you have an instance of it. So in my test bench, I'm just going to make an instance of it. So I'm going to say UUT, which is just, again, a label for, it's a variable name that I'm going to call this instance. It could be top underscore insta 0, just like we did before. But typically, just the way that I like to do it, the way I was taught to do it, is when you're doing a test bench, UUT stands for unit under test. And so I'm going to have top. I'm going to do a port map, and I'm going to label the input switch of top is going to connect to switch underscore signal. I just want to connect those two together. And then my entity here, or my component, says LED for top is my output. So I'm going to have my LED outputs here, and they are going to connect to LED signal. Then I'm going to close that instance, or the port map rather. And there's a little bit of extra code that I have to write here. So what I want to do is have my switch signal get the value of my counter, but my counter is an unsigned number. And my switches are all standard logic vectors. And so those are two different types of data. And so what I have to do is cast my counter as a standard logic vector. And so a standard logic vector is just raw bits, zeros or ones. The counter is treated like a number. So that's the difference. You can imagine that the bits standard logic vector is just switches or LEDs, and the counter adds some context to what that means, what those switches as a group might mean. So you have to cast it here. And then I'm going to begin what we call a process. And a process is it's basically a piece of the code that runs sequentially within VHDL code to a certain degree. You could think of a process kind of like a latch. There is some kind of memory element going on there. But what we're going to do is, in this process, I'm going to wait for 10 nanoseconds, and then I'm going to add 1 to my counter. Then I'm going to end the process. Oop. So basically what this is going to do is every 10 nanoseconds, it's going to increment the value of counter. And then whatever that value is gets put on my signal wire. My signal wire is connected up to my switch input of my top schematic. So if I go back to this, I've got my counter process. It's not really an entity in itself. It's not really an instance like this, but it is an element that lives inside the top. And this is the wire here that is switch signal. And then on this side of my top, that is my switch 3 down to 0 input. And so what I'm doing is I'm counting up whatever that value is, goes on that set of inputs, and those get evaluated by the guts of whatever's inside my top. And then my outputs get read off of LED signal. And if I look here, I can actually see all the guts of everything. So I've got my top test bench file, I've got my counter process, I've got my top component within the top test bench, and then within the top component it has a prime number component and an even odd component, and these are wired up based on their port maps. So this is the overall overarching architecture of our situation here. So going back to our test bench file, I have written the test bench. I've got no syntax errors over here. Nothing is read. So I'm going to click Save. And I'm going to go over here to Run Simulation and click that. And then run Behavioral Simulation. Again, this will take a couple seconds to really process. And then something's going to pop up that is a waveform chart. And this is the set of inputs and the set of outputs that are basically used over time to figure out, is this thing doing what I want it to do, what I expect it to do? Now what's interesting is if I didn't write, for instance, like the correct list of prime numbers, then I'm going to get different weird outputs. You know, if I put 0 or 1 in the prime numbers there, then I'm going to have some interesting results. So I'm going to take this window out just by clicking this little undock button. Each of these has an undock or a float button. And then I'm going to make this window larger so that we can actually see what's going on in here. And we only see a little bit. So what we can do is go all the way back to the beginning by clicking this button. And then this shows you just a zoomed in area. So we don't want the zoomed in area. We want to scroll out, zoom out rather. And now we can start to see some stuff happening, right? What I want to do is zoom out just until I get from 0 to F visible in my window. So I'm going to zoom back in. There we go. 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to F. Perfect. If that doesn't work, you could resize this window. You can actually move some of these values. You can actually drag them up where you want them to go. And if you click this little symbol here, it'll break out each individual bit. So this is how we're going to verify whether or not our code works. So I'm going to look here with this little bar. I just click wherever I want it to go, and these values update based on what that is. So here, my input on my switch signal was 0. So that is the number 0. Then these are my LEDs. So LED 0, if you look back at our LED 0 is connected up to our is prime. LED 1 is if it's even, LED 2 is if it's odd. So I go back here. Is 0 a prime number? No, so that should be a 0, and it is a 0 here. Is it an even number? And the way that we defined it in our code, it's going to give us a 1 here because the least significant bit of 0 is 0, and that gets inverted for our even output if you remember in the code. Is it an odd number? That's what LED 2 defines, and it isn't an odd number. If you notice, even odd, these two LEDs should always be the inverse of one another. And we defined that in our code when we wrote the even-odd architecture. So that looks, just a glance at it, looks correct. Then I can move my cursor over to my input being the value of 1, 0, 0, 0, 1. And so I say, is 1 a prime number? It is not a prime number. Is it a even number? No, it is not an even number. Is it an odd number? Yes, it is an odd number. Move to 2. Is 2 prime? Yes, 2 is a prime number. Is it odd or even? It is an even number, and that's true here. And then for odd, it is false. Move to 3. Is 3 prime? Yes. It's a 1 here. Is 3 an even number? No. Is 3 an odd number? Yes. So I've got true, false, true, or 1, 0, 1 on my outputs. So I can verify this. Now this is what you would do. Maybe you mistyped your list of prime numbers and you have something in here that's not prime, or you have something that is prime that should be appearing that isn't appearing. You go back to your prime number detector code and you could tweak the code there, run the simulation again, and see, does this actually in fact give me the results that I expected? And in this case, it looks like it does. So I'm going to go ahead and close my simulation. You're going to discard the changes to the to your other file there. I just closed the window just to get more space here, and then if I want to go back to the layout that I had before, I go to sources, and that gives me this nice little layout in the pane. So now that I've actually simulated and verified, yes, this thing does in fact give me the outputs I expect based on my inputs. Now I want to put it on the board. So the next steps are, once we have synthesized, we need to run the implementation. And the implementation is going to be basically, as I said before, like when you run a simulation, it actually compiles code, somewhat similar to like a C compiler would do. But when you're doing the implementation and the synthesis, you're actually configuring the hardware. If this were to make transistors on a chip, what would that look like? If this were to program a PLD device, what would that look like? And so all of these different elements are being designed and configured within Vivado as you do the synthesis, as you do the implementation. And so it takes quite a while sometimes for that to happen. You could see here, initializing design, and it will just take a little while for that to happen. So once you've generated the bit stream, you can open the hardware manager by clicking down here at the Flow Navigator window. And the hardware manager will attempt to connect to a board. And we have to allow our board to actually connect to the virtual machine through our actual desktop. So I'm going to plug in the board to USB. You have to make sure that this power switch is activated, otherwise it doesn't work. And there's a demo program running on this board. The demo program just shows all the LEDs in the 7-segment displays, and if a switch is pushed up, that LED turns on. If it's pushed down, the LED turns off. So that's just a diagnostic tool. But once that's available, you know that you can start routing the connection to the virtual machine. So the first step is going into the VirtualBox window at the very top up here to Devices. And we're going to go to USB, and you should see Digilant USB Device. So click on that. You'll hear it disconnect from Windows. And I can tell if it's connected because there's a checkbox there now. The next step is Open Target. You could do this either in the Flow Navigator or the green bar at the top. And I'm going to use Auto Connect. And then the green bar at the top changes, and you can also see this in the Flow Navigator. You can program device. This window will pop up showing you the path to the bit file, which is the actual file it will download. And you can click program, and you should notice a change on the board itself. So once you have downloaded the program, the board itself actually changes. You can see these LEDs here are dim. They're not completely on, completely off. I didn't tell them what to do, so they're just kind of hanging out doing whatever they want to. And these are the switches that I am interested in here. So I've got switch 3, switch 2, switch 1, and switch 0. This is actually what I used in my code. And I also attached these in the constraints file. And you can also see LED 2, 1, and 0. If you recall the functions, LED 0 told whether or not an input was prime. LED 1 shows if an input is even, and LED 2 shows if an input is odd. Currently all the switches are down, and so they are all zeros. So our number is 0, 0, 0, 0. 0 is indeed an odd number. It is not prime. It is not, 0 is even. It is not odd. It is not prime. So now I can switch the least significant bit to 1, and that shows that 1 is not a prime number. It is not even. It is odd. Then I can change this to 2. 2 is your first prime number. It is even. It is not odd. So then I go to 3. 3 is a prime number. It is not even. It is odd. 4, not prime, even. 5, prime and odd. 6, just even. 7, prime and odd. 8, even. 9, odd. 10, even. 11 is both prime and odd. 12, even. 13 is our last prime. Of course it's odd. 14 is even, and 15 is odd.